everyone, I'm Professor Harrison, and welcome back to our module on statistical inference. Today we're going to be covering z-intervals and t-intervals, the two main types of confidence intervals for the mean and when to use each one. We're following Bess, an investigative journalist, on a cold case she can't let go, as she works through two cases that look almost identical on the surface, but turn out to require different applications depending on what you actually know about the data. Today Bess is looking at two files side by side. The first is a large institutional investor that used a confidence interval to report the expected return of a liquid index fund. The approach was correct. The second is a private equity fund of funds that used the same approach on its underlying funds, each of which only had 4 years of return history. The approach was not correct, and we'll find out why. She pulls up her case file. In the last video, we built a confidence interval using the formula, the sample mean plus or minus a critical value times the standard error. What we didn't pin down is where the critical values come from. Today that's the focus, because the answer depends on a question that turns out to matter a lot. Do you know the population variance or not? This will end up being an important distinction because it changes which distribution we're going to be using. Let's start out with a case where we do know the population variance. When the population standard deviation sigma is known, the critical value comes from the standard normal distribution. So, for example, the normal distribution tells us that for 95% confidence, the critical value is 1.96. Here is where that number comes from. You want the middle 95% of the standard normal distribution. That leaves 5% in the tails combined, or 2.5% in each tail. So you need the z-value where 97.5 of the distribution falls below it. You look that up in the standard normal table, or you can compute it directly, and the answer gives you 1.96. For 90% confidence, the same logic gives you 1.645, and for 99% confidence, it gives you 2.576. The structure connects directly back to the central limit theorem. The sampling distribution of the sample mean is approximately normal with mean mu and standard error sigma over root n. The critical value z alpha over 2 marks the boundary that captures the middle 1 minus alpha of that distribution. For 95% confidence, you go out 1.96 standard errors in each direction. That leaves 2.5% in each tail. Then for a wider confidence interval, you go out further. So for 99% confidence, you go out 2.576 standard errors, for example. Now, when is sigma actually known? In practice, almost never, not in the strict sense at least. However, we can treat it as known as long as we have enough data. So for example, if we have decades of data of return history for a major index, then treating sigma as known is a defensible simplification. The estimate ends up being so stable that treating it as known is basically the right call. Here's Bess's first case, the institutional investor. They were estimating the expected monthly return of a large cap index fund. They had 100 months of recent data. The sample mean was 0.8% per month. Based on 25 years of prior history on the same index, they treated the population standard deviation as known at 4% per month. The standard error ends up being 4% divided by the square root of 100. Which is 4% divided by 10, which is 0.4% exactly. The 95% z-interval is then 0.8% plus or minus 1.96 times 0.4%. That's 0.8 plus or minus around 0.78%, so the interval runs from about 0.02 to 1.58% per month. That is a reasonable application. Decades of return history, a liquid and well-characterized benchmark, and a large enough recent sample that the variance estimate is highly reliable. So the z-interval here is justified. Now here's the problem. Most of the time we don't know the true population variance sigma. We estimate it from the same sample that we're using to estimate the mean, using the sample standard deviation s. And that introduces a second layer of uncertainty. You're not just uncertain about the mean, you're uncertain about the spread as well. The z-interval doesn't account for that. It treats s as though it were sigma, as though there's no additional uncertainty from having estimated the variance from the same data. And when n is small, that ends up being a significant understatement of how much uncertainty you actually have. The t-distribution was built to handle exactly this. When you replace sigma with s, the critical value comes from the t-distribution with n-1 degrees of freedom, not from the standard normal. The t-interval has the same structure as the z-interval, but with two changes. You replace sigma with s, the sample standard deviation, and you replace the critical value, for example 1.96, with the corresponding critical value from the t-distribution. The t-distribution looks like the standard normal. It's bell-shaped and centered at 0, but it has heavier tails. The critical values are all larger than their z counterparts, especially when n is small. The interval ends up wider. This extra width is not a penalty. It is an honest accounting for the fact that you have estimated the spread from all the data as well. You are carrying two sources of uncertainty instead of one, and the t-interval reflects both. Here's the intuition for why the tails are heavier. When you estimate sigma from a small sample, sometimes you overestimate it and sometimes you underestimate it. When you underestimate sigma, the standard error ends up too small, which makes your interval boundaries too tight. The t-distribution compensates by spreading its tails wider. With a small sample, your estimate of sigma could easily be off by a meaningful amount. So, the tails are quite heavy. With a large sample, your estimate is reliable, and the t-distribution looks almost identical to the standard normal. The parameter of the t-distribution is the degrees of freedom, n minus 1. You lose 1 degree of freedom because you use data to estimate the mean before estimating the variance. Fewer degrees of freedom means heavier tails. As the number of observations grows, however, the t-distribution will converge to the standard normal, which is exactly why z and t critical values are essentially identical for large samples, and why the choice stops mattering when you have a few hundred observations. To give you a sense of the scale, with 5 degrees of freedom, the 95% t critical value is 2.571. We can compare this to 1.96 when using the z distribution. With 20 degrees of freedom, it drops down to 2.086. By 60 degrees of freedom, it is down to 2, and with 120 degrees of freedom, it's about 1.980. This is only slightly off from the 1.96 that we would get if we used the z distribution. So in general, the reason where the choice between the two distributions matters is roughly below 30 to 40 observations. Above that, the practical difference is negligible. In fund performance work, where you might have quarterly data going back 4 or 5 years, you end up squarely in the region where the difference is real and consequential. Now let's see what all this means in practice. Best's second case is the private equity fund of funds. It has reported that several of its underlying funds have positive expected returns at 95% confidence. Specifically, it reported that one underlying fund's expected quarterly return is reliably above zero. However, the fund only has 16 quarters of data, or exactly 4 years. The sample mean quarterly return was 1.5%. The sample standard deviation was 3%. Here is what the fund of funds actually reported. It computed a z-interval, plugging s into the formula as though it were sigma. So the standard error ends up being the 3% divided by the square root of 16, or 3% divided by 4, giving us 0.75% exactly. The z-interval, 1.5% plus or minus 1.96 times 0.75%, that's 1.5% plus or minus 1.47%, gives us an interval that runs from 0.03 up to 2.97%. The lower bound here is positive, even if only barely. So the fund reported that it confirmed positive expected quarterly returns at 95% confidence. Now let's redo this correctly using the t-interval. The degrees of freedom is n minus 1, which is our number of observations, 16 minus 1, or 15 total degrees of freedom. The 95% critical value from the t-distribution with 15 degrees of freedom is 2.131. The t-interval, 1.5%, plus or minus our critical value of 2.131 times the standard error of 0.75%, gives us an interval that goes from negative 0.1% up to positive 3.1%. The lower bound here is now negative, so 0 is inside the interval. Based on 4 years of quarterly data, we cannot statistically conclude that this fund has a positive expected return. That is the entire difference between the two approaches. The z-interval told investors that the fund had confirmed positive returns, but the t-interval says that the data doesn't support that conclusion. The gap between a z-critical value of 1.96 and a t-critical value of 2.131 is only about 0.17. But at this sample size, that 0.17 difference ends up being enough to shift the lower bound from just above to just below 0. And that actually ends up flipping the conclusion entirely. It's worth noting that in other samples, the same error might not flip the conclusion. If the sample mean were larger relative to the standard error, then both intervals might end up excluding 0. And the z-interval would just be overconfident without actually being incorrect about this conclusion. The lesson is not specifically about lower bounds near 0. It is about reporting a level of precision that you have not actually established. And with short return histories, that ends up being a pervasive problem in fund reporting. In this particular case, the overconfidence was consequential enough to be visible. Often it isn't, and that's what makes the error hard to catch. The decision rule going forward is simple. If we don't know the population variance sigma, then we use the t-distribution. When it is known, however, we want to use the z-distribution. The difference between the two distributions becomes essentially nothing when the number of observations is large, however. So if you have a large enough number of observations, using the z-distribution is fine. In her article, Bess explains this to her readers. A z-critical value assumes the population standard deviation is known. But for funds with 4 years of quarterly returns, it is not known. That simple assumption ends up moving the lower bound from just above zero to just below it. 4 underlying funds in this portfolio cross that threshold when corrected, making it so that the original statements from the fund of funds end up being incorrect. So that's the z and t intervals. Z intervals use the standard normal distribution and require knowing the true population variance, sigma squared. T intervals, however, use the t distribution with n-1 degrees of freedom, and they're appropriate when the population variance is estimated from the data. The t-distribution has heavier tails than the normal, producing wider intervals that honestly account for much of the extra uncertainty from estimating sigma. As the number of observations grows, the two converge and the choice stops mattering. For small samples, however, it matters a lot. So make sure to get your critical values from the t-distribution whenever you have a low number of observations.